challenges, and research directions for large language models inference hardware. We highlight four promising research opportunities to improve large language model inference for data center AI. High bandwidth flash for 10 times memory capacity with HBM-like bandwidth, processing near memory, and 3D memory logic stacking for high memory bandwidth, and low latency interconnect to speed up communication. We also review their applicability for mobile devices. Introduction. When one author started his career in 1976, uh, to 40% of the papers at computer architecture conferences were from industry. Their share fell below 4% at the 2025 International Symposium on Computer Architecture, suggesting a near disconnect between research and practice. To help restore their historic bond, we propose research directions that, if pursued, address some of the biggest hardware challenges that the AI industry faces. Large language models (LLM) inference is a crisis. Rapidly improving the hardware enables AI advances. Projections of inference chip annual sales are 4 times to 6 times over the next 5 to 8 years, while training demonstrates remarkable AI breakthroughs. The cost of inference determines economic viability, and companies find it costly to serve state-of-the-art models, so usage of these models dramatically increases. New trends make inference harder. Recent advances in LLMs requires more resources for inference. Mixture of experts (MOE). The rather than a single dense feed-forward block, MOE uses tens to hundreds of experts, 256 for DeepSeek V3, invoked selectively. This sparsity allows model size to grow significantly for higher quality. Despite a modest increase in training cost, while helping training, MOE exacerbates the inference by expanding memory and communication. The reasoning models. Reasoning is a think before act technique to improve quality. An extra thinking step generates a long sequence of thoughts before the final answer. Similar to people solving a problem step by step, thinking greatly increases generation latency and the long sequence of the thought token strained memory. Multimodal. LLMs have evolved from text to image, audio, and video generation. Large data types demand more than text generation. Long context. A context window refers to the amount of information the LLM model can look at when generating answer. Longer context helps quality but increases compute and memory demands. Retrieval augmented generation RAG RAG. The RAG accesses a user specific knowledge database to obtain relevant information as extra context to improve the LLM results, increasing resource demand. Diffusion. In contrast to the autoregressive method that generates tokens sequentially, the novel diffusion method generates all tokens, for example, an entire image in one step, and then iteratively denoises the image to reach desired quality. Unlike above, diffusion only increases compute demand. The growing market and challenges of LLM inference suggest a great opportunity and need for innovation. The current LLM inference hardware and its inefficiencies. We first review LLM inference basics and its primary bottlenecks on mainstream AI architectures, focusing on LLMs and the data center. LLMs on mobile devices have different restrictions and thus different options. For example, HBM is infeasible. LLMs whose heart is transformer have two inference phases with very different characteristics: prefill and decode. Figure 1. Prefill is similar to training by processing all tokens of the input sequence simultaneously, so it is inherently parallel and often compute-bound. In contrast, decode is inherently sequencer, as each step generates one output token autoaggressive, making memory bound. The key value KV cache connects in two phases with each size proportional to the input-output sequence length. Although together in Figure 1, prefill and decode are not tightly coupled and often run on different servers, the disaggregated inference allows software optimization like batching to make decoding be less memory bound. A survey for efficiency LLM inference reviews many software optimizations. Figure 1. The key processes of inference for the transformer model that is the foundation of LLMs. GPUs and Google Tensor Processing Unit (TPUs) are popular data center accelerators for both training and inference. Historically, inference versions were scaled down from training systems such as the fewer chips or a smaller chip with less memory or performance. Thus far, no GPU and TPU was designed solely for LLMs inference. Because prefill is similar to training whereas decode differs significantly, two challenges make GPUs and TPUs inefficient for decode. Decode challenges. SHA-1 memory. The autoaggressive memory decode makes the inference inherently memory bound, and with the software trend heightening these challenges. In contrast, the hardware tends go in a completely different direction. AI processors face a memory wall. The current data center GPUs, TPUs rely on high bandwidth memory (HBM) and connect several HBM stacks to a single monolithic accelerator application-specific integrated circuit (ASIC). See Figure 2 and Table 1. Nevertheless, the memory bandwidth improved more slowly than compute floating point operation per second flops. For example, NVIDIA GPU 64-bit flops rose by 80 times from 2012 to 2022, but bandwidth grew only 70 times. This gap will continue expanding. Figure 2 is a high bandwidth memory HBM package top view, B HBM side view. So Table 1 are key features of 6 generations of HBM. HBM is increasingly expensive. Looking at one HBM stack, the normalized price of capacity $per gigabyte and bandwidth per gigabyte PS increases over time. PPS over time. Figure 3a shows both grew 1.35 times higher from 2023 to 2025. This rise is because manufacturing and packaging difficulties increase with the dies per HBM stack and dynamic RAM DRAM density growth. In contrast, Figure 3b shows the equivalent costs for a standard double data rate DDR4 DRAM decrease over time. From 2022 to 2025, capacity cost shrank to 0.54 times and bandwidth cost to 0.45 times. While prices of all memory and storage devices surged in 2026 due to unexpected demand, we believe long-term that the diverging prices trend of HBM and DRAM will hold. The DRAM density growth is decelerating. For an individual DRAM die, scaling is also worrisome. Four-fold growth from 8 gigabit DRAM dies that debuted in 2014 will take over 10 years. Four-fold gains occurred every 3 to 6 years previously. SRAM-only solutions are insufficient. The Cerebras and Crocodile tried using full electrical chip filled with SRAM to avoid DRAM and HBM challenges. Cerebras even used wafer-scale integration. While plausible when the companies were founded a decade ago, LLMs and soon LLMs on chip with RAM capacity both had to rate retrofit external DRAM. The figure 3 cost per capacity and bandwidth over time with the trends grind for HBM-A versus DDR-B. A is HBM increasing dollar per gigabyte capacity and dollar per gigabps bandwidth. HBM3E cost of capacity and bandwidth over time 2023 to 2025. DB is DDR decreasing DDR cost of capacity and bandwidth over time 2022 to 2025 and decreasing DDR decreasing dollar per gigabyte capacity and dollar per gigabps bandwidth. Source see appendix. So decode challenge 2, end-to-end latency. User-facing implies low latency. Unlike training that takes weeks, inference is tied to real-time requests, needing a response in seconds and less. Low latency is critical for user-facing inference. Batch or offline inference does not have a low latency requirement. Depending on the application, latency is measured time to completion of all out tokens or time to first token. Both have challenges. Time to completion changes. The code produces one token at a time, so the longer the output, the longer the latency. Long output sequences stretch latency, but long input sequences are also slower because accessing the KV cache during the decode and prefill takes more time. So each decode iteration has a high memory access latency because it is memory bound. The time to first token challenge. Long input sequences and a log increase the amount of work before generation and hence the time to first token. The reasoning models also increase this latency as they generate many thought tokens before the first user visible token. The interconnect latency outweighs bandwidth. Before LLMs, in data center, inference usually ran on one chip, while training needed a supercomputer. The supercomputer interconnect understandably aimed much more at bandwidth than latency. So LLM inference changes the game. Because of a big weight, LLM inference now needs a multi-chip system with a software sharding that implies frequent communication, MOE, and long sequence models further increase the system size to accommodate large language capacity requirements. Unlike training, the size of the network message is often small given the small batch size of the code. Latency trumps bandwidth for frequent and small messages in a big network. Table 2 summarizes the main challenge of the decode inference. Only diffusion needs increased compute and relatively easy to deliver, as it is fundamentally unlike transformer decode. Thus, we focused on a promising direction for improving the memory and interconnect latency, but not compute. The last four rows are research opportunity to fulfill these needs, covered next. Table 2. A summary of the primary hardware bottlenecks for LLM inference and research directions to address them. Check means primary bottlenecks. In the top section of the table, hardware improved drivers. Question mark means a derived interconnect bottleneck for the drivers. For example, if the reasoning models require larger systems to fulfill the memory requirements, it puts pressure on the interconnect latency by increasing the hop count. Likewise, if an improvement on memory capacity or bandwidth allows inference of the same model with fewer accelerator chips, it would help lower interconnect latency for both sections, promising direction. The arrow, the upside, the arrow going upside means pricing the direction that helps with the interconnect latency by shrinking the size of the overall system, thereby reducing the hop count. The fourth research opportunity to rethink LLM inference hardware. The performance cost metric measures the efficiency of the AI systems. The modern metric will emphasize the realistic performance normalized, total cost of ownership, TCO, average power consumption, and carbon dioxide equivalent emission, CO2e, and offer a new target of designing systems. Performance must be meaningful. For LLM decoder reference, high flops on a giant die does not necessarily mean high performance. Instead, we need to scale memory bandwidth to capacity efficiently and optimize the interconnect speed. Performance must be delivered within a data center capacity, often constrained by power, space, and CO2e budget. Power and CO2e are first order optimization targets. Power affects TCO and a data center capacity. The power and energy cleanliness determine the operational CO2e. Manufacturing yield and a life cycle cell embodied CO2e. Next, we describe four promising research directions to address the decode challenges bottom of table 2, although described independently. They are synergistic. An architecture can usefully combine many of them. All improve performance per TCO, performance per CO2e, and performance per hour power. So figure 4, a high bandwidth flash HBF and B 3D computer logic stacking. 1. Bandwidth flash for 10 times capacity. Then high bandwidth flash HBF combined HBM bandwidth with flash capacity by stacking flash dies like HBM Figure 4a. HBF delivered 10 times memory capacity per node to reduce system size to save power, TCO, CO2e, and network overhead. Table 3 compares HBM to HBF to HBM and DDR and low-power DDR, LPDDR DRAM. The weaknesses of alternatives are bandwidth for DDR5 and capacity for HBM, and write limits and high read latency for HBM. For HBF and another HBF benefit is sustainable capacity scaling. Flash capacity continues to double every 3 years while, as mentioned above, so the DRAM growth accelerates. Two well-known flash memory restrictions must be addressed. Limited write and endurance. Write erase cycles can wear out flash. Therefore, HBM must hold infrequently updated data, such as weight at a different time or slow changing context. Page-based reads with a high latency. Flash reads are at page granularity 10 second kiloparsec with a latency 10 kilobytes with a latency substantially worse than during microseconds. Small leads reduce effective bandwidth. These issues mean HBF cannot replace all HBM. A system still needs a normal DRAM for data unsuitable for HBF. Table 3. A ballpark comparison of the HBM, HBF, HBM, and DDR, LPDDR, and Flash. The addition of HBF enables exciting capabilities for LLM inference. 10 times weight memory, weight share fusion during inference. So HBF's 10 times capacity could host many more weights, such as giant MOEs, to enable much bigger models than affordable today. 10 times context memory. Limited write endurance makes HBF infeasible for KV cache data updated for every query or generation token. However, it works for a slow changing context. For example, a web corpus used by the LLM search that stores billions of internet documents. A code-based database used by AI coding that stores billions of lines of code. A paper corpus used by AI tutoring that tracks billions of research papers. Smaller inference system. Memory capacity determines the minimum hardware to hold the model. HBF downsizes the system, helping communication, reliability, and resource allocation. Greater resource capacity. HBF would reduce dependence on HBM-only architectures and alleviate the global shortage of mainstream memory devices. HBF opens new research applications. How can software deal with limited write endurance and page-based high latency reads? What should be the ratio of the traditional memory to HBF in a system? Can we reduce the constraint of HBF technology itself? How should HBF be configured for mobile devices versus for data centers? 2. Processing near memory for high bandwidth. Processing in memory, PIN, conceived several decades ago, obtained high bandwidth by augmenting memory dies with small and lower power processors attached to memory banks, while PIM offers extraordinary bandwidth. Key challenges are of software shading and memory logic coupling. The former limits the number of software kernels that run well on PIM. The latter hurts power and the area efficiency of computer logic. In contrast, processing near memory (PNM) is a technique that places memory and logic nearby but still uses separate dies. One version of PNM is 3D computer logic stacking (C3). Unfortunately, some recent papers blur the distinction between the PIM and PNM. They use PIM as a general term whether or not the computer logic is placed directly into memory die. We go here with a simple but sharp distinction. PIM refers to a design where the processor and the memory area are in the same die, and PNM means that they are done nearby but separated die. This distinction makes the PIM and PNM unambiguous. The hardware advantages are irrelevant if it is hard for software to use, which is our experience for PIM and data center LLMs. Table 4 lists the why PNM is better than a PIM for LLM inference, despite weaknesses in bandwidth and power. Specifically, PIM requires software to shard memory structure of LLMs into many small pieces that rarely interact to fit into 32 to 64 megabyte memory banks. Shards in PNM can be 1,000 times larger, making it much easier to partition LLMs with a low communication overhead. It is also unclear if the compute can be sufficient in PIM, given the very limited budget for power and thermal of a DRAM technology process node. The table 4 PIM versus PNM for data center LLM inference. Why PNM is better than a PIM for data center LLMs? The comparison is not as clear for mobile devices. Mobile devices are more energy constrained and run LLMs with many fewer weights, shorter context, smaller data types, and smaller batch sizes to a single user. These differences simplify the sharding, reduce the compute and thermal needs, making PIM's weaknesses less problematic and so plausibly viable for mobile devices. Third is the 3D memory logic stacking for high bandwidth. Unlike 2D hardware, where memory IOs reside on the shoreline, 3D stacking, see figure 4b, instead uses a vertical through silicon vias TSVs to get a wide and dense memory interface and for high bandwidth low power. The 3D memory logic stacking has two versions. Compute on HBM based style reuses HBM designs by inserting the computer logic into HBM based die. Because the memory interface is unchanged, bandwidth is the same as the HBM, while power is 2 to 3 times lower because of the shortened data path. Custom 3D solutions enables bandwidth and bandwidth per watt higher than using the HBM through using a wider and denser memory interfaces and more advanced packaging technologies. Despite better bandwidth with low power, and 3D stacking faces challenges. Thermal. Currently, a 3D design is harder than a 3D as there is less surface area. One solution is to limit flows of the computer logic by running at a low clock speed and voltage, as the LLM decoder inference already has a low arithmetic intensity. 2. Memory logic coupling. An industry standard may be required for the memory interfaces of a 3D computer logic stacking. The 3D stacking opens a new research questions. The ratio of a memory bandwidth to the capacity or the computer flops is significantly different from existing systems. How can software adapt it? Imagine, imagine a system with many memory types. How do we map LLMs efficiently? How to communicate with other memory logic stacks and a main AI processor if necessary? What a trade-off in the bandwidth, power, thermal, and reliability for various design choices. For example, compute die placed on top versus bottom, the memory die count per stack. How do these opportunities change for mobile devices versus data center LLM accelerators? 4. Low latency interconnect. Techniques 1 to 3 help latency as well as throughput. Higher memory bandwidth reduces latency of every decode iteration, and higher memory capacity per accelerator chip reduces system size, saving communication overhead. Another promising latency directions and of data centers is to rethink the network latency bandwidth trade-off, since inference is more sensitive to interconnected latency. For example, high capacity topology. Topologies with connectivity, such as tree, dragonfly, and high dimensional theory, require fewer hops, reducing latency, and these topologies may diminish, 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 diminish bandwidth but improve latency. The processing in network communication collectives are used by LLMs, broadcast or radius, and MOE, and dispatch and collect are well suited for in network acceleration to improve both bandwidth and latency. For example, a tree topology with in-network aggregation enables both low latency and high throughput or reduce. The AI chip optimization. The latency-focused inference is a chip designed with several possible optimization. Storing a small arriving package directly into an on-chip SRAM instead of the off-chip DRAM. Placing the computer engine close to the network interface to reduce transportation time. Reliability. The co-designing reliability and interconnect can help both. A local standby spare reduces system failure and the latency and throughput consequences of the migrating the failed job to new healthy node somewhere when there are no standby spares. If the perfect communication is unnecessary for LLM inference, one can reduce latency yet deliver satisfactory quality result by using fake data or a prior result when a message timeout expires, rather than waiting for a straggler message to arrive. Related work. High bandwidth flash. SanDisk first proposed HBF, an HBM-like architecture for flash to overcome its bandwidth limit. SK Hynix later joined its development. Microsoft researchers proposed a new class of memory that focuses on read performance and high density instead of write performance and retention time for AI inference. While not specifically mentioned, HBF is a concrete example of the proposed new AI memory. Another research paper proposed integrating flash into mobile processors on a on-device LLM inference enhanced with a LPDDR interface for low bandwidth needed a prefill and a processing near flash for the bandwidth need of the decade. Processing near memory. 3D computer logic stacking has gained increased attention as a technique for bandwidth higher than the HBM, such as compute on HBM-based dies proposal and an AMD concept. In the non-3D space, Samsung AXDIMM and Marvel Structura A attach processors to commercial DDR DRAM. For former integrated computer logic in the DIMM buffer chip, the latter leveraged the CXL interface for improved programmability and ease of the system integration. A survey paper provides more examples of a PNM or PIM. Many papers discussing using PIM, PNM in mobile devices, not the main focus of this paper. The low latency interconnect. Numerous papers describe low hop count network topologies including trees, dragonfly, and a high-dimensional theory. This magazine's 20 reference limit prevents citation. Examples of commercial processing in network are NVIDIA NVLink and InfiniBand switches that support in-switch reduction and multicast accelerating throughput SHARP SHARP scalable hierarchical aggregation and reduction protocol. Similar capabilities for AI workloads appeared recently in Ethernet switches. Software innovation. Besides this paper focus on hardware innovation, there is a rich space of software hardware co-design for algorithmic and software innovation to improve LLM inference. For example, a root cause is the auto-progressive nature of the transformer decode, so new algorithms that avoided auto-regressive generation, such as diffusion for image generation, could dramatically simplify AI inference hardware. Conclusion. The increasing importance and difficulty of inference for LLMs and which desperately need lower cost and latency is an attractive research target. Auto-regressive decode is already a major challenge for memory and interconnect latency, which is exacerbated in MOE, reasoning, multimodal data, RAG, and long input sequences. The computer architecture community has made great contributions on the challenges and a realistic simulator was available as it has previously for branch prediction and cache design. Since the primary bottleneck of the LLM's inference are memory and latency, a roofline-based performance simulation could be useful to provide first-order estimate in many scenarios. Additionally, such as frameworks should track memory capacity, explore the various sharding techniques that are critical to performance, and use modern performance cost metric. We hope academic researchers will respond to the opportunity to accelerate AI research. The current AI hardware philosophy, full reticle, die with flops, many HBM stacks, and bandwidth optimized interconnect is a mismatch to LLM decoding inference. While many researchers explore compute for data centers and will recommend instead improving memory and network along four directions: HBM, PNM, grid stacking, and low latency interconnect. Moreover, the novel performance cost metric that focused on data center capacity and system power and carbon footprint offer new opportunities versus conventional measures. Constrained version of the HBM, PNM, PIM, and 3D stacking also might work well for mobile devices LLMs. Such advances would unlock the collaborative work toward important and urgent innovation that the world needs for delivering affordable AI inference. Acknowledged and references. An appendix. DDR DRAM prices 19 57 to 2024. Authors and okay, authors. And this is appendix table. Okay. Today I read this paper, Challenges and Research Directions for Large Language Model LLM Inference Hardware. Thank you for your time. See you next time.